I'll begin this afternoon's session with a brief introduction. Welcome to the Canadian Institute of Forestry's National Electronic Lecture Program. My name is Sharon Young, and I will be hosting today's session. Today is Tuesday, February 4th, 2025, and this is the first session in the e-lecture series entitled Advances in Operational Forestry, Tree Planting, and Carbon Mitigation Research. This series is brought to you by the Canadian Forest Service and Canadian Wood Fiber Centre. The CIF-IFC is very pleased to collaborate and host these webinars. For today's session, we are pleased to have Carolyn Smyth, who will give an exciting presentation titled Post-Fire Restoration and Adaptive Planting, Linking Future Fire Projections, Carbon, and the Bioeconomy. To kick things off, Dr. Carolyn Smyth is a research scientist with Natural Resources Canada. Her research includes greenhouse gas reduction scenarios for Canada's forest sector, including forest ecosystem modeling, harvested wood product tracking, and substitution benefits of using wood and bioenergy sources. Scenarios also include future wildfire management and opportunities for the bioeconomy. With that, I will now pass it over to Dr. Carolyn Smyth.
Thank you so much, Sharon and Tanisha, for organizing today's events. It's a pleasure to be here. I'm attending actually from my home in Victoria, and today is a snow day, which is unusual. But my home is situated on the traditional lands of Lekwungen-speaking people. So for today, it's my pleasure to kick off this part of the series and talk about fire and carbon and the bioeconomy. And there we go. I'll actually start with a bit of a carbon 101, and we'll talk about the forest and forest sector carbon cycle. So shown is an image from the State of the Forest report from a few years ago, and it shows all of the fluxes associated with the forest. And you can see arrows of different color. The green arrows show growth. So carbon is taken up out of the atmosphere and included into forests as the trees grow. Now, when the trees die, they can decay, and that releases carbon back into the atmosphere. But we can also release carbon during fires. So fire can have a direct emission, but it can also kill the trees and have a delayed emission as the wood decays. Now, if we move over in this picture, you'll notice deforestation. That is another source of carbon that can put carbon up into the atmosphere. And deforestation is a land use change. So it's switching from a forest to a cropland or a settlement, for example. And the reverse, afforestation, can occur, where carbon is being taken up by new forests. For harvesting, we can have direct emissions from harvesting, often associated with burning. So burning of the bark to generate energy, or burning of residual waste left in the forest. But not all of the carbon from harvest is emitted. Some of the carbon is transferred, and the transfer occurs are shown in orange here. So carbon is half wood by dry weight. So, sorry, wood is half carbon by dry weight, and it's stored in the product for as long as it's used. And when the product is discarded, it can either be burned, which releases carbon back into the atmosphere immediately, or it can be transferred to landfills and decay. And we also have carbon that's transferred when there's mortality in the trees, and it's stored in the carbon. And so it's stored in the soil. So the dead wood in the soil will decay over time as well. So we need to consider all of these fluxes and storage pools when modeling forest sector carbon. And we often look as to whether the forest is a sink of carbon, whether it's removing carbon from the atmosphere, or whether it's a source of carbon. It's emitting or releasing carbon to the atmosphere. So that's just a bit of a primer on the forest carbon cycle. Now let's talk about wildfire. So I'm showing an image of the area burned, and those time series are orange bars, as well as the greenhouse gas emissions associated with those wildfires. And this is from a science policy note looking at greenhouse gas emissions from wildfires. And it's for the managed forest. And the managed forest is shown in a little inset here in the green colored forest areas. And there's two things I'd like to point out in this image. One is that there's a very strong correlation between the area burned and the greenhouse gas emissions. And there's very high variability as well. Some years have a lot of fire and a lot of greenhouse gas emissions. Other years don't. Now, in this time series, which goes up until 2022, the peak year was 2021, where almost 300 million tons of carbon dioxide were released from the fires. To put that in context, emissions from all other sectors in Canada are around 700 million tons. So the emissions associated with wildfires are quite large. And in 2023, we had even greater area burned than in 2021. And the emissions from that fire season will be even larger. So we have a lot of greenhouse gas emissions coming from wildfires. And my job for the past 15 years or so is to look at how we can reduce greenhouse gas emissions in the forest sector. In order to do that, we need to consider the various activities and sinks and sources that we have the opportunity to change. So this image is from one of the websites looking at forest carbon, and it indicates a systems approach to looking at greenhouse gas reduction. So we can do activities that will increase the carbon sequestration, so pull more carbon out of the atmosphere. We can do activities that reduce carbon emissions. That can be reduced slash pile burning or reducing wildfire emissions. And we can also increase carbon storage on the landscape, store carbon longer in wood products as well, and have recycling. So there's various activities that we can look at through a systems approach to look at forest, wood products, and then replacement of high emissions materials and high emissions fossil fuel burning. So where do we start? Well, we often start with a workflow. And this is a workflow that we put together with colleagues from the US and Mexico. And it describes how we go about modeling greenhouse gas reduction. And it starts in the upper left with the goal. We wish to reduce the amount of greenhouse gas emissions in the forest sector. And we'll start by considering policies and interests, programs. We'll get together data sets that we can use in the modeling, and then we'll establish a forward-looking baseline against which we can compare our activities. We'll then develop scenarios that describe a change in behavior or technology that's designed to reduce greenhouse gas emissions, and we'll do the modeling. After we've done the carbon estimates, we can consider risks and costs and change to forest resilience. And then we can summarize that result and synthesize the activities and their impacts. And then there's here a revise and reflect and reassess. So we'll often, and I have repeated this loop many times, and every time you go through this loop, you learn about the impacts of a different activity that you can model. Now, I'd like to point out where risk appears in this diagram. So risk is occurring after we have modeled the greenhouse gas emissions. But if the risks are high, then they would come more to the forefront. So they would be considered early on. And I'll describe to you a journey that we've gone through, really improving the way we include wildfire in the carbon modeling. And part of that is really understanding the future risks. So it started back actually in 2017. In 2017, we were doing an analysis for BC, looking at GHG reduction of a variety of different activities. And there were large fires in 2017, roughly 1 million hectares burned. And the image on the right shows the smoke associated with those wildfires, as well as the location in Canada and the US. And the fires were so large that they affected the landscape, the harvest, the conservation scenarios that we were modeling. So we had to redo the analysis. And at the time, we had a very simple assumption about future fires. So we redid all of the analysis, and we were finishing up in August of 2018. And a 1.2 million hectare fire season was in full throw. So we then understood that we would have to get a much better handle on modeling future fire. We couldn't just keep redoing all the simulations every time we had a bad fire season. So we set about improving the future fire modeling and considering risks. Specifically, we were interested in conservation scenarios because that was the question at the time. And people were also asking about the bioeconomy, looking at post-fire restoration, trying to understand how much salvage harvest potential there was. It was only later, actually, that we started looking at wildfire management scenarios. So I'd like to tell you about that first set of questions, how we responded to questions on the bioeconomy. And to do that, we use a systems approach. So we consider how can we minimize the net emissions to the atmosphere. And that includes the forest ecosystem, as well as the services used by society. So we can have bioenergy and wood products. We can have burning of fossil fuels and other emissions-intensive materials. And we said, what would happen if we were to do a scenario looking at post-fire restoration? So we're going to model the future wildfires, and after a wildfire occurs, in a baseline, we don't do anything. In a restoration scenario, we would salvage, harvest, and replant. And we'd replant a commercial timber species. Now, fortunately, we were working with Juha Metsäranta, who had included future wildfires in a previous risk assessment. And so we were able to use those methods to model the future fires. And I'll tell you a little bit more about that later on. So here's the way we set up the analysis. We have 3 different models. So we have a carbon budget model that looks at the forest ecosystem. We have another model that tracks the carbon and wood products. And then we have a third model that considers substitution benefits. When we modeled the forest ecosystem, it was a Monte Carlo approach. So we modeled 100 different wildfire futures. Mostly because wildfire is highly variable. From one year to the next, you can get a very large change in the area burned. In the restoration scenario, we restricted salvage harvest to suitable and accessible areas. I'll explain how we did that. But once we had the salvage harvest, we had 2 opportunities. We could use it in a mill and create products, or we could use it in a community and create bioenergy or biofuels. And so we wanted to explore both of these opportunities. So I'm going to start with products. So when we modeled the future salvage harvest, we recognized that many areas that burned would not be salvage harvested. They wouldn't be accessible or perhaps not suitable. So roughly 1/3 of the provincial forest is available for harvest. And we considered road access for the suitability of doing salvage harvest. So it had to be accessible by being close to a road. It also had to be suitable. So we considered a softwood or coniferous leading stand that had good site productivity. So it was more likely to be salvage harvested. And when we did that, roughly about 14% of the burned area would be salvage harvested. So if we think of all of the area that burned, only a small percentage would be salvage harvested. And a lot of these constraints are practical and economic constraints. They're not carbon constraints. And another economic constraint we considered was haul cost. So it's challenging to work with salvage wood, and you have to work with it quite quickly after a wildfire because it tends to dry out. So we considered how costly would it be to transport the salvage harvest to a mill. And the map on the left shows the map of BC along with different squares to show the 28 mills. And this is a subset of all of the mills in BC. And the different colors show the haul cost to go from the cut block to the mill. And you can see there's large areas where there's no salvage harvest. So this would not be considered suitable or accessible for salvage harvest. In the colored areas, we would salvage harvest and transport to the mill. And we found the haul costs varied across the province. In some places, they would have access to a lot of salvage harvest, but it'd be quite expensive to transport. And the southern parts where the mills were closer together, there's some mill competition, and the haul costs would be cheaper. So this helped us understand the spatial context of where the harvesting would occur. But we also estimated the cumulative net reduction in greenhouse gas emissions if we were to do a post-fire restoration scenario relative to doing nothing in the baseline. And we find that it does reduce the emissions, but it's fairly modest. So it was 44 megatons over about 50 years. And it had a wide range. And the range reflected the range of the variability in the fire. So the fires are quite variable. The salvage harvest and the timing is quite variable. And the GHG reduction is also quite variable. So this really helped us understand a little bit better on how to model future wildfires when we're using salvage harvest for products. Now, instead, we could use salvage harvest for bioenergy or biofuels. And we looked at bioenergy mainly for heat. We tend to find more of our fossil fuels are used for heat. And also liquid transportation fuels. And what's great in BC, we have community level data on the fossil fuel use for various communities. So in this map, it has colored bars that show for a given community how much heat demand there is and what types of fossil fuels that they're using. So we know in Vancouver, for example, they have a lot of natural gas, a little bit of fuel oil that's being used for heat. So with this information, we could understand the GHG reduction of using bioenergy in place of fossil fuel burning. And we found actually the major centers would be a big draw for the bioenergy because they have such high heat demand. So a lot of the biomass would be going to larger centers like Prince George and Vancouver. And is there a GHG reduction? Yes, it's smaller. And again, has quite a range because fire has quite a range. But it's also a little bit hard to predict 50 years into the future. We don't exactly know how our fossil fuels would decarbonize. But it does seem like there's a possibility to reduce the emissions in some cases. So I'll just summarize this part. The first question was about bioeconomy, and we were looking at post-fire restoration for products for energy. And so we set up our three models, and we found that future wildfire is highly variable, and that has to be a huge component of the model. We found that if we focused on bioenergy, we'd mostly be looking at areas with high heat demand. And in fact, biofuels would start to take over as heating decarbonized. And biofuels are a hard to abate sector. And then the other option was to create wood products. And if we do wood products, we're not entirely sure how the mills could handle a highly variable supply of lower quality wood. And so the economics would become a bigger part of this equation. And I think one of the next talks deals with some of the economics on the fire. So this was a big learning experience for us, trying to understand future wildfire modeling in the context of GHG reduction scenarios. So we got our feet wet with looking at post-fire restoration, but then we started thinking about wildfire management scenarios and how could we reduce the wildfire emissions. And if we look through the various scenarios in the literature, we can find scenarios related to planting fire-resilient species, as well as reducing risk. And reducing risk could be targeting high-risk stands for harvest. It could be reducing the fuel loads, either through thinning and prescribed burning or prescribed burning alone. And there's also other scenarios that we haven't included because they don't fit our model very well. But it's looking at reducing human-caused fires and fire breaks around communities to reduce the connectivity of forests. And those are interesting scenarios, but we focused on the planting fire-resilient species and reducing risk. Now, what's interesting about the wildfire management scenarios is that typically there's a short-term increase in the emissions. So thinning and prescribed burning, for example, would increase the emissions in the short term, but there would be a payback, if you like, when the fire comes and does not burn severely. So instead of having a high intensity stand replacing fire, you would have a lower severity fire and may in fact burn more area. So there's the short term, long term, that's an interesting question. And I had two fire ecologists that gave me very different opinions on this. One said that carbon is the elephant in the room. The emissions created by the activities are so large that it may not work. It may not reduce the emissions. And the other said it's a no-brainer. The wildfire emissions are so large that treatment, in fact, would reduce the emissions overall. And I thought, great, this is a perfect question. When we don't know the answer and you get two opposite opinions, that's lovely. That's when we want to try and figure out what's happening. So where do we start? So we started with planting fire resilient species. And we also assumed that they would, or we also imposed that they would be climatically suitable. So we want whatever we plant to be able to grow into the future. So in terms of the fire resilient species, we followed the stocking standard guidance from the province. And they've identified the first tier of seed selected species, so Douglas fir, western larch, ponderosa pine. And then a second tier would be white bark pine, balsam poplar, and aspen, and black cottonwood. So we understood from this list what species to plant after harvest and salvage harvest. And then we tried to identify if these species would be climatically suitable using a climate change-induced species selection tool from Will and Colin in BC. And so from this short list of species, we actually found an even shorter list that would be climatically suitable. And that looks like this. So the graph is showing the area by species. And the baseline is the dark green, so it has a lot of lodgepole pine as well as spruce. And the fire resilient climate adaptive planting mostly pulls out Douglas fir and aspen and reduces the amount of pine and spruce. So we're able to put this in the model and layer on the wildfires. And we assumed that the wildfire severity would be reduced if we planted a fire resilient species. That's a pretty big assumption. So we wanted to be able to show that that assumption was valid. So that meant, again, improving the fire model. So we did improve the fire modeling and brought in a fire behavior prediction system. But we also expanded back to the national level. And we've done national level GHG reduction analysis before, and then we did a lot of work in BC, and now it was time to go back to the national level. And it's really great that we have access to remotely sensed data sets that are spatially explicit that we can put into our generic carbon budget model. So we're able to use historical disturbances, remotely sensed wildfire and harvest. We're able to use forest inventories on the age and species. We have simple assumptions on yield tables that describe how the forests grow. And then we have a baseline assumption where we do nothing after wildfire. And we have a restoration assumption where we do salvage harvest and replant. And we have to forecast harvest into the future using Quebec Chief Forester's forest management tool. And then we have to forecast future wildfires based on the previous system. And I'll show you what that looks like. So this was a big challenge to go spatially explicit, but it allowed us more opportunities for examining the wildfire question outside of BC. So how do we model fire? So what the model needs are projected maps of the area that burns, and we're modeling out to 2070. And so we're using the past to inform the future, and we're assuming that the area burned increases due to climate change. And we're fortunate to be able to build on a lot of the work that's been done by the fire ecologists. And they have created different zones that are shown in the map that represent homogeneous fires, so that the zones describe the fires of that region. And the darker colors in this map show higher cumulative area burned over time. So some areas have more fires than others. We wanted to be able to reflect that in the carbon budget model. So we look at the area that's burned in the past, we fit it statistically, we increase the area that's burned in the future, and then we simply place it on the landscape. And at first we had randomly placed it. Now we're starting to weight it by the ignition occurrence to make it a little bit more realistic. I'd like to show you what this looks like rather than going through a lot of the methodology. So I'm going to show you an animation. There's going to be above ground biomass on the right. Don't worry about that. We're going to focus in on the disturbances on the left. And wildfire historically is shown in the yellow, orange, and red colors. Pests are purple. And then the harvest, which is hard to see, is black. And this is going through the past. These are fires that have occurred on the landscape. And as I mentioned earlier, 2023 was one of the worst years. Oh, I didn't get that right. Hang on. I don't know if I can get it back there. 2023 was one of the worst fire seasons that we've had. With roughly about 13 million hectares that burned. And that's what the fires look like on the landscape. Now that's the last year of data. Now we move to projecting, forecasting what the fire will be. And you'll see often the projected shapes on the landscape are ellipsoidal. We assumed a very simple shape. And you'll see actually blue colors as well. And those indicate the areas where we could do salvage harvest and replanting. So it's in areas that are eligible for harvest. And for young stands, we might just do underplanting and not do salvage harvest. But this gives us a way to model fires into the future with different severity classes and to do restoration activities. And so developing this framework to look at post-fire restoration nationally was a huge jump, but it really allows us to understand and model some wildfire management. And in order to improve the fire modeling, we're including the fire behavior prediction system, which includes fire weather variables, which are available, and allows us to look at different severity classes of the fire. And we're able to use this prototype system to estimate the greenhouse gas reduction in the next 50 years. But we only did it for one future wildfire. And we know fire is quite variable. So we would need to do a whole other set of draws to understand the actual greenhouse gas reduction range. But we have a prototype system that we can use to model these things. Now, there was one more thing we wanted to do, and you can probably guess that was improve the wildfire modeling. So it's really been a journey of trying to improve the wildfire modeling over and over again in the carbon modeling. So we had assumed earlier on that post-fire restoration, if you plant a fire-resilient species, it will lower the future wildfire severity. And that's an assumption. And then we brought in the fire behavior prediction system, which has fuel beds, which just allows us to categorize the fire into different severity classes. But if we have species-specific planting, we would like to have species-specific fire impacts. So we'd like to understand the combustion and mortality associated with burning particular stands. And so to do that, we have embedded the Canadian fire effects model into the carbon budget model. So it receives information on the fire weather, the fuel beds. It receives information on the stand, the age, the species, and we're able to estimate the mortality and consumption for a fire. Now, we really like this flexibility. And CAN-FIRE has been linked with CBM previously. It just hasn't been linked inside a module. But having the dynamic landscape in the carbon budget model means you understand the fuel loading and can pass that to the fire model. So it's a way to link a fire model and a carbon model. Now, there are other ways to do this. We could put a carbon model into a fire model. We could go back and forth between fire and carbon modeling. So the carbon model would generate the landscape, be passed to a fire model. You could model the burned area, pass it back to the carbon model. You could do that too. So there's three different options. We're carbon modelers, so we put the fire model inside the carbon budget model. And this will help us understand the greenhouse gas emissions associated with the fire. And then I think my question that I haven't fully answered is how do we express the fuel beds and the characteristics of treated stands within the fire effects model in order to represent the future wildfire severity on a treated stand? So that's a tricky question. And that's what we're grappling with now. Okay, so I'm going to summarize, and I've taken you through this journey of looking at the bioeconomy, looking at wildfires, improving wildfires in the carbon model, and really have been exploring kind of the fundamental concepts and components that we need to do the forest ecosystem carbon modeling and be able to model forest and wildfire management. And it's very important, I've emphasized this several times, but the system approach is necessary to look at greenhouse gas reduction. It's not just about the forest, it's also about tracking the carbon and wood products and considering how the forest sector interacts with the energy sector. So fossil fuel burning, and also interacts with other materials. So what are the substitution benefits? And finally, the overall goal, of course, is to compare mitigation activities for forest and wildfire management in order to improve the climate-effective bioeconomy. So I do want to note there's many people involved in this analysis. It's not just me. I will thank all the co-authors. So Max, Juha, Scott, Ben, Michael, Sheng, Werner, and of course the rest of the carbon accounting team. But many students helped me with this work. And a couple now, Christina and Devin, are staff, and other students are Tristan, Amy, Finnerty, Paulina, Jen, Lucas, and Marie. And consultants, Nick Walsworth and Simon. And finally, I'll acknowledge support from the CFS, from the Forest Innovation Program, as well as the Pacific Institute for Climate Solutions, Wildfire and Carbon Project. And I'll stop there and say thank you very much for your attention.
Thank you, Carolyn. That was a great presentation. Now let's move on to the questions. While we wait for the participants to finish typing their questions, I'm going to launch the post-webinar survey. Just give me 1 sec here. Just a reminder that there are 2 questions, so you may need to scroll down to see the next one. Hey, Caroline. The first question for you is, how close are you to the point where model can be scaled down to prescription for a specific forest management area?
Okay. Not entirely. Let me take a guess at where you're going, and you can correct me if I'm wrong here. So I think you're suggesting if we were to do thinning and prescribed burning on a specific FMU in the country, would we be able to understand the impacts when future fires come? So we can certainly do half of that. We can model the thinning and prescribed burning and have done for a long time. You know, the carbon budget model is quite good at that. Understanding the future fire impacts if and when that stand burns is the tricky part. And understanding how frequently you have to retreat that area. So after 10 years, do you have to go back in? After 15 years? That part we haven't quite figured out as well. We can take some simple assumptions. And then the overall treatment area, I think, is the other part. So we'll make simple assumptions on how to do that. But if we can be better informed by activities that are happening on the ground, that would certainly help. And then that last piece is really changing the CAN fire to be able to understand it's a treated fire model and have equations that change the fire intensity. So it's not a slam dunk, unfortunately, but it's the area that we're in right now. And if
Thank
I
you,
didn't get your
Caroline.
question, Robert, just correct me. I kind of guessed where you were going.
Thank you, Caroline. The next question for you is, did vehicle access factor into your model for reforestation so far? So for areas where there are no roads for planters to access the site, access would need to be by helicopter or by building rough trails. Were any access considerations included?
Yeah, that's an excellent question. So it'd be very expensive to do helicopter planting, and very difficult to build rough trails for planting. So we did consider for BC access to roads. That was part of the suitability and accessibility constraints. When we did the national modeling, we only did ownership, so whether or not it would be available for harvest. But since then, we've brought in the road networks and have a buffer on the road network. Now, exactly how big that buffer should be, that's a good question. So we're modeling 50 years into the future. Obviously, more roads will be built. So I think we're assuming a 50-kilometer buffer right now for roads, but we could certainly change that. It would reduce drastically the amount of area that we would have for reforestation activities. So there is a nice balance there, and maybe a sensitivity study would be the best way to figure out what that impact would be. But excellent question, thank you. It's certainly a constraint that has to be considered.
Thank you, Caroline. So Rob just posted another question in the Q&A pod, and he said, Caroline is correct about assumption. How about prescription at provincial level?
Yeah, that's a good question. So the province for us is just divided into different forest management units. So we often do generic assumptions for a province, and then you're filtering it down into the FMU levels. So that's possible. I think it's more the physical constraints rather than the administrative boundaries. And I do recognize that the guidelines change from one province to another and one territory to another. But we tend to do it without barriers in our scenarios at first. And then later on, we consider economic constraints, and later on, we consider technical constraints. So whether it's actually possible. So I think the general answer is yes, as long as we remove some of the barriers, and then actually it's being imposed at the FMU level.
Thank you, Caroline. Next question for you is, I saw one chart or map that had a rehab option separate from a salvage option. Please elaborate planting without salvage.
Yes, thanks. Yeah, I didn't clarify that well enough. So we look at salvage harvest if the stand is over 40 years old. And we'd like to impose at the national level a site productivity grade as well. So we know that salvage harvest has enough constraints already that it probably would be an older softwood stand that would be considered. But it is possible to do underplanting for young stands that have burned. And so we had just called that rehab, but that's what we mean. So stands that are under 40 years old, we would underplant and could change the species, but we wouldn't salvage harvest. So it would have a very different fire risk, I think, than if we did salvage harvest and replanting. And hopefully that's picked up in the fire models.
Thank you, Caroline. Before we wrap up, I'd like to remind everyone that this session is being recorded, and the recording will soon be posted on our website on the Open Access e-lecture page. All right, if there are no further questions, I would like to bring this session to a close. Thank you all for participating in our CIF electronic lectures. And once again, thank you very much to Caroline for the great presentation. Bye, everyone.
Thank you. Bye.